Hey, thank you, everybody. I'm really happy to be here, and thanks all for coming and listening to me today. This is not so much a class as it is. I want to bring you in a journey that I took over the last couple of months on rebuilding an old SCSI controller that used to be really rare, let's get started. So I want to tell you, I didn't do this alone. Every good project is comprised of a team, and in this case, the team was comprised of Chris Hooper and me. Chris is both of us are originally firmware engineers. We met in the Bay Area. Chris is also the founder of a company called DSSD, and I'm working for Google as an engineering manager. We have a number of open source projects that we both worked on. A lot of my career I spent on firmware projects like Coreboot, OpenBIOS. I did some work a long time ago on UAE, the Amiga emulator, and Chris worked on a version of the Berkeley fast file system and built his own version of the RGB to HDMI, some of which you may know. So what is this project about? We're building basically a brand new Zorro III SCSI controller. And this project, during the whole lifetime of the Amiga, there were only really 2 Zorro III SCSI controllers ever built. Zorro III is the bus that powers the Amiga 3000 and the Amiga 4000, and is significantly faster than the Zorro II bus that it precedes, with, in theory, it being a direct competitor to PCI. In practice, the implementation is not quite as fast as the original PCI versions, but it was getting pretty close. So what we're doing is, this card is also supporting DMA. It supports the FastSCSI 2 protocol, which in theory supports 10 megabytes per second. I know, it's not very fast today, but back in the day, this was a killer card. The card was originally designed for the Amiga 4000, had pretty hefty hardware requirements in terms of the latest bus controllers. So it needs a Buster 11. Well, I'm saying minimum. There's rumors out there that we might see a new one any year now. There's also, the card is powered by an NCR 53C710 chip, which was a state-of-the-art SCSI controller chip at the time, and it supports auto boot through a ROM. So you plug into your Amiga and you can boot right off the hard drive. So how does this start? How does anybody start doing a SCSI controller, right? Well, the answer is, of course, because we can, right? The way this started is the pandemic happened, and I started learning soldering because I had a lot of time in my garage. And in addition, I spent a lot of time chatting on Akel Paul Resendez's Discord server and found a guy, Chris Hooper. Turns out he lives 7 minutes away from me, which was ideal. So every time I ran out of parts in the early pandemic, I was like, hey, Chris, can you come over and bring me a 74 F32 or something, right? Chris would bring it over. I would do the same thing if he got stuck. So that was the beginning. We did both like smaller projects. And then I would say by accident, I got an A4091 SCSI controller on eBay. These things were extremely rare. Like you see one every couple of months pop up, maybe every couple of years these days. And so the card, it was only like the seller lived in Germany, which is where I'm originally from, and so he wouldn't send it to the United States, so I sent it to my mom's house originally. And then it sat there for most of the pandemic until finally, like in August last year, I was able to go home and visit my mom and pick up the package. So here's a rough timeline. So it's been a project of like the last 6 months, roughly. And so why now, right? Like why build this in 2022? So if you look at it, the prices really, like for all of these Amiga boards that you can buy on eBay or Amiga, they've really skyrocketed, right? And why? Because they're incredibly rare. Nobody makes this stuff. They're hard to get by. People now all have decent jobs. We all pay a lot of money for this stuff. But it shouldn't be like that. It should be available for everybody, right? On the other hand, also, I got pretty inspired by other folks in the Amiga community, namely Paul Resendes and John Hertel, who worked on a number of reverse engineering Amiga products, like reverse engineering the Amiga 4000 mainboard and reverse engineering the Amiga 3000 and a number of others, bringing like a lot of old machines back to life that died because the electronics went bad or the batteries or capacitors ate through the main boards. And I was like, well, I'm not the guy to build like a complete Amiga from scratch, but like maybe I can do something like a SCSI controller, right? And then of course there's like one important thing to this whole story. It's the Dave Haney files, all right? Like Dave has published all of the logic files for the GALs, the little SPLDs that are powering this board as source code. And so you can download them today, recompile them, put them on a board, and it'll work. The other card that I mentioned out of the two that exist, that logic is all secret, and most likely if these cards die, it's lost forever. So with all that going on, like the idea was really like, hey, can we create something that's like open and accessible, right? And like all of these things, like if you're looking at the Amiga today, you're not looking for getting the latest power machine that like features your nice 3D graphics and your latest games, but you're probably looking to learn something, to feel nice about the past, and to figure out, because all this stuff is so easy compared to what computers are doing today, you can look at it and you can understand it, right? So that was one of the aspects why we started doing this, really, and putting something out there at future generations maybe, or if it's whoever is interested, really, you can look at it and say like, oh, this is how this worked. And also, these guys that built the Amiga originally, and particularly also the 4091 SCSI controller, they've done an amazing job. And a lot of the work that is happening today, like a lot of the work that I'm doing, I got into computers because of the Amiga, or stuck with computers because of the Amiga. A lot of what I have done in my career wouldn't be there without this stuff. So it is a little bit of a tribute also to the shoulders of the giants upon which we stand. One thing that came to be in the, like as the project moved along, we started looking at this and we're like, hey, we gotta like build a SCSI controller, right? What is the first thing you think of? It's like, let's build a PCB. There's lots of PCB projects out there, especially during a pandemic, this has exploded, right? Now, the next thing though is like, oh wait, this thing has a custom bracket. And then there's like, maybe also other stuff that was when you used to buy the product 20, 30 years ago, you got a box and a manual and an install disk. And so what really tickled my fancy there too was to create something that is not just like, here's a PCB, go and solder it yourself, right? It's like, can we create something that's really like end-to-end? That you look at it and it's like, hey, this looks like what you would have gotten back in the day. So that's how this journey started. And it started last August by me traveling to Germany and meeting my mom, and she was like, son, I haven't seen you in 2 years. Let's eat a lot of German food. And as I mentioned, retro computers are cheap in Germany. Cheaper, much cheaper than here in the US, particularly in the Bay Area. So I occasionally ordered something to my mom's house, and then I occasionally ordered another thing, and well, 2 years later, I had forgotten about this a little bit, right? Like how much actually might have happened. I got home and my mom had like built this tower of stuff. Honey, don't look at this. Well, coming back, I met Chris, and I said, hey, Chris, we got to build a SCSI controller, right? And it's like, how do we go about this? Okay, we got to take some pictures of the thing so we can like map it out and figure out what's going on. And my first thought was, hey, we can put it on my printer and just scan it and we'll get high-resolution pictures. Well, that was a fail. I didn't put those pictures on there because they were just like completely dark and not sharp. And so we figured out a number of ways with cell phones and other stuff and stitched the pictures together. It turned out pretty well. And then we sat down in the garage and took a multimeter. And basically the way this works is you look at, you try to figure out roughly what the schematics should look like. But in the end, if you reverse engineer, there's only one way of getting through this. You measure every single connection between every single pin on the board. And that's what we did, and we started writing it down. It took us weeks and weeks and weeks, and sometimes, like, this is something that really was enormously helpful to do this with somebody else, because sometimes you just start fading off and go like, oh, did I measure this one already, or did I forget about this one? Is it really connected to that pin? If somebody else listens and writes, and then you do a shift, it goes a lot better, believe me. And of course, sometimes we were not quite sure what's going on, like under the chips and on the other side of the board. And so I started taking the logic chips off and started looking at what's under there, and we started looking at the traces. And then we started making schematics, right? And so basically what happens is, in the past, there were 2 revisions of this board. Revision A was made by Commodore early on, and they built PCBs, they got it almost working, and then they had to ship it in a rush. And so there were a bunch of budge wires on the board, roughly like a dozen or so. So it's quite the adventure if you get one of these early on cards. And then for revision B, because Commodore was not trying to be, I guess, in the business of building SCSI controllers, there was this company, DKB Software Incorporated, which then produced this board for Commodore. And what they did was they routed the budge wires. They put the budge wires onto the inner layer. So this is a 4-layer board. And so on a 4-layer board, what do you do? Like if you start reverse engineering, right? How do you figure out how the board is routed? Well, one way, and I believe that John Hertel did this for the ReAmiga project, is that he sanded down the PCB and until he saw the inner layers, and then he drew them up, and that was it. Now, it hurt my soul to do this, all right? I can't say it differently. I did not want to destroy the one original working board that I had because it was rare and I didn't know if I would get another one, and who knows, maybe I need to measure something later on in the project. So destroying this one thing would have been a really bad idea. Well, gladly we got a lot of this done just by shining a flashlight through. And because literally we found out that it was only the bodge wires that Commodore had added that they routed through here. So you can see this in the picture here. It is actually, if you're using a flashlight and you're shaking it around a little bit, you can see it much better than on the picture, but it's hard to put this in the picture. And then once we actually figured out all the wires, right? So this is what it looked like. Each one of these blue lines is one of the connections that we measured. And then we started placing the components as close to the original. And then we started routing also as close to the original. And this was one of our goals really for this version of the card, to create something that is as close to the original as possible. Of course, there's like these days you would, if you built this from scratch, right, you would optimize some things. You would maybe make the card shorter so it's cheaper or whatever. Like there's ways to optimize this, but the first version that we built, we wanted to make it authentic. And the one thing, however, that we didn't keep authentic entirely was clear labeling, because we wanted it to be easy to build. So if you look on the back side of the PCB, all the caps that are soldered on there say their values between the pads. So you cannot see this once it's assembled, but it's on the board, just to make it easy without having your documentation in front of you at all times. And this is what the final board then in the first version looked like. As a EDA software, we used Easy EDA. Easy EDA is, I always found it weird to do this stuff in a web browser. And mind you, I work for a cloud company, but this was kind of like I started out using KiCad, and I thought that was pretty nice. But one of those things, like with Easy EDA, it is fantastic for collaboration. Like Chris and I, like even because we would not get together very often during the pandemic, when we did, it was kind of troublesome, and so we could do this at the same time while he was at his house, I was at home, and so we were working, and we always had the latest version of what the other person had put in, and we could communicate about this very easily. So this was a great way. Now, let me tell you, for manufacturing, it turns out it hasn't been the best thing ever, because getting easy ADA files to certain manufacturers is a little troublesome. As long as they take Gerbers, that's great. But some folks want more than Gerbers. They want the original files, especially when you go into manufacturing the cards. And this gets a little tricky. But that's still a journey we're embarking on. So let me talk a little bit about the level of detail, all right? So there's one of the things that DKB added was this little seal over there, and so we did exchange the seal and put our own initials in there. We did update the timestamp. I think it's at 93. We updated it to 2021. But other than that, like we really tried to get very, very close to the original board, and including, we found this, like when we started looking at the board under a microscope, and we found this little tail hanging off one of the vias, we were like, is there something wrong with the board, right? Like, what's going on here? Like maybe this cap might have leaked and eaten up this trace, but no, it's just like a little tail that's left. So I don't know if Dave, I think he's not here right now, but like if I meet him, I want to ask him. It's like, what's that appendix for? I mean, quite frankly, these guys, when they built these boards back in the day, right? Like they drew this stuff up by hand, and then they erase parts and like redraw it. And at some point, it's like, this is good enough. That's what I'm thinking, where stuff like this is coming from. But yeah, they didn't have all the fancy tools that we have today, where you have. So we didn't use an auto router at all because we wanted the routing to be identical. But in theory, if you build something from scratch, obviously, like you have an auto router available, and stuff like this would not happen, right? And you move something around, and it gets rerouted, and everything looks nice all times. Well, at this point, a short stop to say thank you, really, for the people that have been helping with this project. And first and foremost, obviously, Dave Haney, who was originally working on this board, and for really make this possible. But also, I want to say thank you to Simon Gosk, who is the guy rebuilding Amiga cases. He lives in the UK. I think he's originally from Poland. And I started chatting with him about this project, and I was like, oh, like, how would you go about building custom brackets? And he's like, I know how I would go about it. I would talk to my boss, and I would ask him if I can have his machines for a couple of days, and I would do this. And so I was like, well, I don't have a boss like that. Could you maybe actually ask him? And so he did, and this was a big help. Tim Iyer, who was also a big help for the project. He has one of the few remaining manuals of the Amiga 4091, and he sat down and scanned it, and he did a fantastic job. Like the manuals, the original manuals, they were really flimsy. I'll show you in a little bit. And of course, Jeff Brace for answering my late night panic calls last night. Thank you, Jeff. So brackets, right? The first thought was, hey, we can 3D print something. That'll be good enough. And so we made like a little model, and this, basically what's going on is you cannot use PCI brackets that are more readily available, because on PCI the back of the card is on the other side. And so these are basically just inverted, mirrored versions. But then also most cards anyways don't have this large to where you screw your hard drive against. Right? And so turns out you can 3D print something like this. It works. It's around here. It gets a little bit tricky. This is the original bracket that I took off the board. But it's better to make something. And this is a photo that Simon sent to me from the production line. So they were all laser cut and then bent. And I had long discussions with him, because he was like, this double bend that you see there to keep the pins safe. It's like, can we optimize that away and just put a hole in? And I was like, well, yeah, that would work. And then it's like, but can we try to do it anyways? Because it would look much closer to the original if we had that double bend. And so these double bends need a lot more sophisticated machinery, basically, is the problem. And of course, at the same time, we also try to do this ourselves. Chris built this bracket over there, and you can tell, like, without the machinery, your bends look a little more round than they should be. And this is the 3D printed version. It looks nice, but if you look at it at the wrong angle, it will fall apart, and certainly won't hold your hard drive. One thing we did then was like some post-processing when we got them. So we put like some foil on the inside and protected the outside, so that like if for whatever reason any parts are touched on the board, you don't short circuit the board and destroy it. Another challenge we ran into was the artwork. All right, so pretty much nobody has these boxes anymore. When you buy something on eBay, you get a board in like a silver sleeve, right? And that's it. Now, Big Book of Amiga Hardware has some pictures, and For the original that Commodore built, this is the best picture that I could find. It's like 700 pixels. You can not make out a whole lot of detail on any of this stuff, and certainly not get the dimensions of anything, right? And well, DKB, when they built the board, they did different packaging. I'm gonna ask you, which one do you folks think looks better? You like the DKB one? I thought, for my taste, the DKB one was like a little too colorful and peppy for the time. So we went with this one. Well, as I mentioned, a complete project end-to-end is not possible if you don't have a manual, right? So the original manual had 3 different languages, was like almost 100 pages. And in the scan, you can see it, well, this one's from a 1200, so it's not exactly the same, but you can make it out here, like the pages were almost translucent. You see all of the color from the next page blend through, and when you scan these pages, that is also what you see. So when we got the scans from Tim, we did a bunch of post-processing to get really the quality up. Chris did a fantastic job. Also, like the front cover and the back were completely redrawn to have an even higher quality. And so one of the things that we had to do to keep it affordable, because trying to print a manual in 3 languages and almost 100 pages gets expensive pretty quickly, and it's more of a gimmick. So we cut out everything but English at this point. And on the other hand, I have to say the new manuals actually look a lot nicer than the original Commodore manuals. So that's one positive aspect of the whole thing. And yeah, like it originally started out also with, we were like, hey, we should just like scan it and print it and then cut it and fold it. And now we're both firmware engineers. Firmware engineers and cutting hundreds of pages of paper does not work super well together. So it kind of worked, but it never looked great. So we had somebody do it, and with only 1 language, it's actually quite affordable. Well, the box. The box was a different kind of challenge because really nobody has this box left. We didn't have a good guidance on like how big does this thing have to be, right? There were obviously, we also couldn't get any scans, and so we only had to go off pictures. And what we did was we measured the card, and if the card was in the same picture with a box, we extrapolated between the card and the box. And then we're like, okay, at this angle, it's probably gonna be this high. And I think we got pretty close to the original. And then you draw it up in some web-based software, and when you order them, and then this is like me assembling all the boxes in my little office room at home. Yeah, if like, I definitely have to say, like, building one of these is fun. If you're building like 30 or so, it starts looking like this pretty quickly. I think this is only like 15-ish right there. Another thing, so we had the boxes, right? And I was like, hey, all the original boxes, they have some sort of foam material in there. Like, what do we do? So I found on AliExpress, I found this fantastic noise dampening foam that you can order, and people were complaining about it online because it comes in a box, probably like this size. And it's very flat when you want to put it in a shower, and like with a shower head, you shower it off, and then it goes like, right? And then it becomes bigger. And then you have this giant thing that you can see in our shower over there. And of course, you got to cut it. And like once it was done, our cat, Katsu, she loved the foam pit. She was all over it. I spent another hour or 2 trying to get all the cat hair back off again. Yeah, and then finally, like, our PCBs arrived. And the first one we built 5 PCBs. We ordered 5 PCBs. So we were like, it's just a proto build. It's not going to work anyways. Let's start building this. And that was hindsight is 2020, obviously, but that was kind of a mistake because it turned out the boards worked all along. And buying only 5 is, of course, like not as economic as buying 20 or 30. So I assembled the first board, and it looked good, and we stuck it into the machine, and nothing happened, right? One of the things that happened was that I did a little mistake. We tried to power on the board first, and we attached a lab power supply, and we burned one of the ROM chips that we put in there. And so one of the pins, the VCC pin, fell off of the chip. We didn't notice it. These are rookie mistakes, really, but like this stuff happens if you've never done this before. So it's going at it with a lab power supply, not the best idea. I'm not exactly sure even how we did that. We figured that part out because we saw like the card wouldn't show up, and that's because all of the identifying information is not in the logic like on other cards, but it's in the ROM itself. And so if the ROM is dead, the card is just like never gonna show up to the system. We fixed that, then the card did something. It showed up once, right? And that was it. And that day we stopped and we were like, we did it. We got it working, yeah, right? Well, next day we were like, okay, let's attach a drive to it. And it's like, wait a second, this thing's not booting. And once you're actually like in the operating system itself, the card is also not there anymore. It just vanished from the bus. So what did we do? I plugged in Diagram, which has like a little more diagnostic functionality to look at Zorro cards. Diagram started endless looping because something was off. And so we were like, oh, so it's, what seemed such a win yesterday was a big fail the next day. That sucks. So we got a little serious there. We got our logic analyzer from Cellier out, which is like a nice little box. It has 16 channels, so you can check a lot of signals at the same time and compare them against each other. It's still a little tight for the Zorro 3 bus. You cannot look at all the signals at once, but at least it gave us some idea of what was going on. Now, what was going on was the Amiga just stopped talking, right? Like at some point, it was like, look good, look good, look good, and then silence on the bus. So we made a bunch of assumptions originally, and I want to talk about this because building a project like this, you're guessing, right? You're guessing, 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 and then you're verifying as you move on. And so in terms of the GALs, the logic chips on this board, the original 4091 used a -10 and -15 parts. My assumption was, naively, I buy Atmel parts that are all -10, and it's just gonna work because you can always go faster. You just can't go slower, right? And then I don't have to worry about what I solder onto the board, in which order. And the original 4091 also had not only GALs, but also PAL-CE chips. The -15s were all PAL-CE. And of course, I thought, because I had built a 3660 before the CPU accelerator board, that the ATF 22V10 is like a fully compatible replacement. Well, more on that later. Also, we looked, in terms of the ferrite beads, we looked at the Amiga 4000 schematics because those were open already. And they use a lot of 600 ohm beads. So with ferrite beads, the inductivity is measured at 100 megahertz, which when you just measure them like as a part, it's basically just like 0 ohms or whatever, right? So that's So we had no idea, coming into this, we had no idea how to even measure this. So we had to do some research. It's like, how do you know what's on the board? And we assumed it's like, whatever, stuff we get on eBay or stuff we buy from Mauser is all the same, more or less, we hope, right? But as this smart guy, Albert Einstein, a long time said, assumptions are made, and most assumptions are wrong. And he proved to be, that assumption was correct. So we had to get a little more serious. We were looking, all this logic analyzing didn't get us anywhere, right? Like, just the signal looked good on the logic analyzer. My skills on the oscilloscope were not good enough at the time to actually see if the signals were like at the right levels or like slightly off, but still like in scope for the logic analyzer. So my hunch was like, hey, how sure are we? Because we took a big guess with those Farad beads. What if those Farad beads are off? And so at some point, Chris was like, hey, I got this a nano VNA. It's a very small network analyzer. I don't know how it works, but I got it from a previous job. Like, I read somewhere that you can measure these parts with them. So we started, it's like, how do we measure these parts? Okay, we got to take them off. So I made this list. I desoldered all of the parts, stuck them on a piece of paper, drove over to Chris's house when he had figured out how to do this, and we started measuring. And then as you can see, like right around 100 megahertz, all these curves make like some weird bump, right? And we were like, what is up with this? Like, we must be doing it wrong. Well, now it turns out the nano VNA is like a very cheap piece of equipment. They're like $80. And for the most part, it's accurate. Just like production, because of the way they're designed, they have this problem at 100 megahertz that stuff becomes inaccurate there. But we didn't know. We thought like, hey, maybe the parts are broken, maybe whatever. Like, so this is the nano VNA, and one of the things you can see down there, actually, like that little antenna thing, is if you want to measure these parts, right, you have to solder them to the probe. And so that's a lot of work if you're sitting there soldering and then desoldering and soldering and desoldering and not being sure if you're actually doing the right thing. And you have to calibrate every single time you do a measurement before, because the antenna, the length of the antenna will have significant impact on what you measure. Well, it's a good thing to have friends with better equipment. So thanks God we had a friend with a $30,000 real network analyzer, and that helped us get the curves look a lot nicer, all right? It also confirmed that the original measurements were not that bad, so we could have just stuck with that. You don't really need the expensive equipment if you want to do something like this. But I wanted to put that out there. It's like sometimes when you're looking at these things and you're debugging and you're feeling stuck, getting a confirmation like that can just push you over the problem. So what came out of this, say, if you look at this curve, right? We put 600 ohm Farad beads on there. Well, ours are in a range of like 60, 70 ohms here. And so that was one mistake. Basically, by the time you get to 25 megahertz, which is what the card is clocked with, these 600 ohm beads, they were just drowning out the signal and it was gone. Just enough to be a problem after a couple of iterations. So first thing I did was I soldered on 0 ohm resistors, and then later real Farad beads. You just like say like, hey, the noise on the bus is not as bad as like completely killing the signal. And it worked. And so we, for the first time, like the card survived multiple reboots, was visible in the operating system, and saw disk drives. Yes. So we did some tests. Originally, I only took down the resistors, the beads for the Zorro signals, and then the card would work stable with SCSI 1, but not SCSI 2. We did the same thing. We were like, well, maybe Commodore or DKB used 60 ohms for all of them, right? So we tried that, and indeed, I measured some more, and indeed, what came out of this was that the card would work at full speed. Now, full speed, in this case, the card does not do a Zorro 3 burst mode, so the speed is limited at around 5.1 megabytes per second at the moment. That's where the community comes in, hopefully. Somebody that understands programming logic and writing GAL code a little bit better than me. Please, if you do, come talk to me. All right, so the card worked in my 4000. I plugged it into a 3000 and it stopped working. And then we took the original card and Chris took it home and put it in his 3000. It worked like a charm, right? So it's like, okay, the original card works. What did we do wrong? So we went through the schematics again, measured again, went over it. Well, it wasn't any of that. At some point, I took all the gals off of the original card and put them in our cards, and the card started working in the 3000. So it was our chips that were the problem. Right? So what's the problem then? Like, because we have the source code. Did we maybe compile the source code wrong? Right? Or is it something with the chips? Are the chips bad? So I'm like, okay, no, we bought them from Mauser, so they're not probably cheap fakes or whatever. They should be working. A little glimpse at the data sheet will tell you that the Atmel parts have significantly shorter propagation times internally. And so one of the things that we learned is that the logic of this card does its timing implicitly through the propagation delays of the parts. And so if you use too fast parts, the card will just not work. That's still one that, well, the solution to it was like to use a bunch of slower parts in certain positions. So two of the parts now have to be slow parts and all the others are fast parts. We got it working and it's reproducible, and we always test like all of the cards in both in the 3000 and the 4000. But it's not a good explanation, right? So that's definitely an open. Of course, I had to put this one in because Austria is pretty close to my homeland, Germany. We had, of course, like the design has under like the plate where the hard drive is mounted has a terminator that comes with it. It's an active terminator. There's not much magic to it. One of the things, like if you ever decide that you want to build one of these, the design is such that you have to Dremel out the PCB. Please Dremel carefully. Like you can destroy both of the boards if you do that. And make sure that you clean it. It makes a giant mess. Yeah, of course, end-to-end, right? I said that. Let's make some disks. And if you remember, like I said, the best picture that I found of all the collateral was that low-resolution picture on Big Book of Amiga Hardware. Well, there is no better picture of the disk than that, of the original. And so I was looking at this stuff, and I still haven't found any, so this is the best guess I could do. Actually, I know that on the original disk, as it is in the picture, this logo is not there, but it's on like the manual, and I decided to derive a little bit. It's not very accurate, but the disk right now with like Amiga OS 3.1, 3.2, whatever, you don't really need the disk anyways. Like we're developing, we put a little test utility for the card on there, like our so-called factory test, where you can test functionality of the card, like test the jumpers on the back and test throughput and test that the card is generally working. So we put that on there together with the original files. The original files are good if you want to use Amiga OS 3.0. But it's in the box. And then cables. Wow, cables. I did not think about that being a problem. And of course you can make your own cables, right? And it gets tedious pretty quickly if you're sitting there making 30 cables or whatever. So we try to figure out folks that would like make the right cables and the right size. And turns out speaking Chinese is a very big advantage if you negotiate with AliExpress vendors. And so one of them actually did make these cables for us specifically. Yeah, and then like once we had the first boards working, we got a larger batch of 25, and so we started buying components, right? And this time we got a stencil and components in reels now, and not just like the little packages. And then Chris, this is Chris, that's me over there. That's my workstation. Chris brought his microscope. So that was another point of contention when I started putting basically 2 factory line stations in the garage. It's not necessarily the best to keep peace in the house. Certainly, one suggestion to all of you, be careful when you start talking about pick and place machines. Well, all that fun aside, while we were building this project, one of the fun things that happened too is we built a bunch of other stuff to make debugging or working with this easier, right? And so one thing is like the 28C256 EEPROMs are easier to get, they're cheaper, and they're reflashable without like having to have a ultraviolet light. So working on a driver, we decided that we're gonna like make a little adapter. Many people have built these adapters. I found out after I made one myself. But it's easy stuff. These are more interesting. They're like interposers for the gals, because as you could see on the pictures before, like attaching probes to the gals is a little bit painful if you have to do it on and off in a lot of them. So these come like you can put either a PLCC socket on the bottom, then you can plug it on top of like a non-socketed chip, or you put a plug in the bottom and then you put it in the socket and then the original chip on top, and then you can connect your probes here. It's a lot easier. Other custom stuff. Simon, for us, he also designed these SCSI to SD carriers, so you can mount your SCSI to SD directly on the card. In this case, it's an original card where I tested it. And like if you want to go that route, like you can 3D print your slot brackets. At some point, when we open source the whole project, we'll put the STL files in there. It's okay, but they're fragile, so don't tear on them too much. Another really cool thing, because we were like, hey, what if, right? Like the gals that are part of the card, the original card that I got, they were all protected. What if they changed stuff and it's not in the Haney files? How would we know? We can't read them. And they're PAL CEs, so the other like reverse engineering options in the field didn't work with this one. So Chris decided to build a brute force PAL decoder, which analyzes. It actually doesn't only decode PALs, you can put any logic chips in there and it'll basically tell you what's in there. It's quite nifty. It needs a little bit more work for more complex stuff, but it was useful during the development process. And then some fun pictures here, actually. Like, when I put the quartz, typically I would put like little pin headers through the holes and then put the quartz in, so I could ultrasonically clean the boards and take the oscillator out. On this board, I had completely forgotten, for some reason, to solder the 4 pins in. And because the fit was so tight on the first revision of the boards, the card just worked fine. And we found it later when we were like, wait a second, this still looks very golden and not as silvery as we anticipated when we were inspecting the boards. And then here, this is one of our attempts. There's around, I think, like 40-ish farad beads on this board. So if you start having to rework all of them, it's a little bit of a pain. Make sure that like you check your parts numbers and get the right parts if you want to build something like this. Well, closing in on the end, the drivers, right? So there's a driver coming from Commodore. The latest released version, 40.13, works just fine on the board. We've seen in the wild copies of version 40.20, and then this guy in France, Cosmos Amiga, he published a patched version of 40.13 that fixes a couple of bugs. This guy's a genius. Like, he will like binary patch like all of the like 30-year-old drivers, whatever. But for me, that's like a little like stressful to do. So looking is like at drivers that are out there, right? Like, there's like some of the code will be written in assembler, and like some is in C, and then there's this other thing, because the SCSI controller chip that's on the board is actually like its own CPU, more or less, and it can run its own code. And that code needs to be compiled with the NCR script assembler. And like, it took, I don't know, probably like a month to find an old copy of this. Like, this was tricky. There's also various open source versions in the Linux kernel and in the BSD kernel. Both of them don't really work well. Well, the one in BSD is a lot better than the one in Linux. The original driver does not support NSD or TD64, so theoretically, no disks larger than 4 gig. Now with 3-to-1, you can switch that limitation off, and that works. But manual intervention is required there. Now, it's really unfortunate, right? Like, 3-to-1 is out, and it supports the Amiga 4000T, which has exactly the same chip, except that chip is directly on the main board of the 4000T and not on the Zorro card. So whoever is working on that one could just recompile the latest version, and it would work great with all of these features that are missing from what's out there. But with the current situation of the Amiga community and like the legal situation about the operating system source being unclear, I doubt that that is going to happen in the near future, at least. So what do you do? Well, I like this saying: if it's not open source, it's a waste of time, right? One of the reasons why we built this thing is because we want to make it available, and we want people to be able to learn from this. So Chris, I started talking to Chris about this, and Chris is not one to listen and then not do anything. So he immediately started rewriting the driver based on existing NetBSD code. He is using a more modern driver design where he decouples like device partition table and handling in separate tasks in a way that basically, like what happens in these old drivers, right, is that the partition table of the system needs to be parsed by every single storage driver. So there's a portion of code that's copied into each of these drivers. Now, our idea is we can split this out into a separate task and have the actual hardware driver talk to that task, more like a modern Linux or BSD system would do it. So if anybody's working on another storage controller, please talk to us and adopt this, because it will allow us to fix mistakes across the board and add support for other stuff like MS-DOS partitions and stuff, or UEFI partitions these days. Now, the driver supports large drives. The speed, we're not quite there yet. The original driver is 5.1 megabytes per second. This one is 4.2. We're catching up. We have to do some more work on this, but we're definitely getting there, right? Just to put, this is our factory test tool that Chris wrote, and you can see on the left side, there's like our driver now, and on the right side, there's the original Commodore driver. It's a little bit too small, but just to tell you, like a lot of this stuff is just like either implemented wrong in the original driver or it's not implemented at all. So we're trying to really modernize the whole thing. So, stop talking, right? Like, we want to see some hardware. So I have the hardware up here. You guys can come up and look at it or whatever. I'll also have a table in the exhibition. Please stop by, come talk to me. I did not bring my Amiga to actually plug it in and demonstrate it because that was just not doable overnight in the airplane from San Francisco. But the card is there, and I can definitely try to answer all of your questions. Yeah, and then the future, like what could we do, right? So one thing that is definitely going to happen next, we're going to open source the whole thing because that was the plan all along. We hope that people will be inspired by this, just as I was inspired by the work of Paul and John, and maybe people will start improving what's there or build their own or just glance at it and say like, hey, this is neat, glad it's out there, right? One of the things that would be really nice to have is support for Zorro 3 burst. That would, with a simple PAL upgrade, GAL upgrade, would improve the speed of the board by a factor of 2. It is unclear if any workarounds on a board would have to happen. So I saw in the original GAL code that Dave Haney published, there are traces of Zorro 3 burst mode in there. They have been replaced. I believe it was because of some issues on the 3000. I hope to find out more. If you know, please come and tell me. Of course, if one were to build future versions of the design, like get rid of those 8 different GALs, put them in one single larger CPLD, you'll save a lot of pins, you can make the board smaller. Or you leave the size the same and you add some RAM to it or something, right? So there's also folks working on open source RAM upgrades for Zorro 3. Together with something like the storage solution, this would be an ideal thing. You could directly DMA into the onboard RAM and get like much higher transfer speeds. Of course, with the open source driver that is also happening now, we could use more modern SCSI chips that could do. So the 720 and 725 are still 6830 bus friendly. So they're easy to integrate. They're not pin compatible, but other than that, they're drop-in replacements, right? You gotta like cut the board in half, forget about mounting the SCSI hard drive to the board. I wouldn't recommend that particularly anyways, to be honest. But like in that case, like people have already asked me and said, hey, I could use this with a mediator, I could plug a PCI card in the end, and then the SCSI controller in the front, and that would work. It's definitely possible. We talked about it, it's unclear, probably we're not gonna do a whole lot of work on the hardware design after we open source it and just give it out to the community and see what happens. But there's a lot of ideas, and stuff like reducing the size of the board is not particularly hard or challenging, right? And then, well, whatever you would like to see, please grab the stuff, work on it, make it better. This is what this community is all about. And with those words, that's it.